Hello there, Mr. Sutton bringing you this lesson on exponential growth and decay. In this one, we're going to solve real-life problems involving exponential growth and decay. For your warm-up, see if you can express the following as a differential equation. Over time, a positive quantity y grows at a rate proportional to itself. All right, let's see how you did with that. So we're saying that the rate of change of y, dy dt, is equal to, well, the quantity times some k value. If it's growing at a rate proportional to itself, that means that the derivative is just going to be y itself times some constant. So here's how we can express that. And then go ahead and see if you can find the general solution to this differential equation. So to do this, we need to do some separation of variables. We don't see any t's out here, but we can at least divide both sides by y to get that with the dy. And then this dt, let's put it over here on the right side to go with the k. Taking the antiderivative, that's going to be ln of y equals kt plus c. Now you might be wondering, hold on a sec, don't we have an absolute value in the ln? Well, they did say y was a positive quantity, so we've already taken care of that before we even started. To get y by itself then, we have to raise e to both sides. So we have y equals e to the kt plus c. And we could actually go a little bit further. So when I'm adding exponents together, I could really think of this as e to the kt times e to the c power. Now, we're going to fudge this a little bit. E to the c power, c is a constant, e is a constant, so e to the c is just one big constant. I'm just going to call that big C and stick it out in front of my e to the kt. So this c isn't really necessarily the same constant as this c here, but it is a constant, and that's all we really care about at this point. Now here's the other thing we kind of care about. What kind of growth is this if you have a constant times e to some power? Oh yeah, that's exponential growth. I mean, it's the title of the lesson, but still, it's a revelation, isn't it? So this might remind you of a formula you saw in pre-calculus. This was your continuous compounding formula, the PERT formula. In that formula, P was your starting amount. Same thing over here, except we're calling it C. C is your initial amount. It's the y value when x equals 0. In the old days, R was your growth rate. Now it's going to be K. And then T is still time. That hasn't changed. Now that we've got that background on the relationship between differential equations and exponential growth, let's try it out on a problem. So during the exponential phase, E. coli bacteria in a culture increase in a number at a rate proportional to the current population. So there's that proportional to the current population language again. If the growth rate is 3.2% per minute and the current population is 199.0 million, what will the population be 9.9 minutes from now? So you could start with the differential equation. However, if you recognize exponential growth based off of this language, you can actually go straight to y equals ce to the kt and skip that whole differential equation dance. So you do you. Pause the video and see if you can solve this one. All right, so I'm going to skip to y equals ce to the kt. Again, I recognize this rate proportional to the population language. So let me plug in what I can here. Now, what am I ultimately solving for? Well, they want to know the population 9.9 minutes from now. That's going to be this y value here. So that means that we need to plug things in for c, k, and t. So for the c value, that's going to be the initial population, the current population anyway. They said that was 199.0 million, so I'll put 199 in for that. And then for the next two things here, we'll do this in a couple steps here. So let me first write a general equation that I can plug any time into, and then I'll plug in the time. So let's get my k value next. That's the growth rate. If they're giving me 3.2%, I just need to convert that into a decimal. So that's going to be 0.032. So we've got e to the 0.032t. And now to get the population 9.9 minutes from now, we just need to plug 9.9 into t and see what happens. So there's what I'm ultimately going to be plugging in my calculator. And now let me go to the calculator. So here we are on Desmos. Let's do 199.0 if you like, e, and then exponent button. And we're going to have 0.032 times parentheses 9.9. And let's see what that gives us. We've got 273.173 if we round that off. And that's going to be in units of millions of bacteria. So as a follow-up question, what would we do you think, if we wanted to find the population 9.9 minutes ago? Pause the video for a quick moment and see if you can puzzle that out. All right, so if we want to go 9.9 minutes ago, we just need to use negative time. So we would do negative 9.9. And if you wanted to do that on the calculator, you could. We could just change this to negative 9.9. And that long ago, we would have had like 144.967 million bacteria. On this next example, let's read it out here. So atmospheric pressure decreases approximately exponentially as elevation increases. So we've definitely got an exponential sort of problem. They spelled it out for us. If the rate of decrease is determined to be 12.5% per kilometer, at what elevation is the pressure 1/2 of the pressure at sea level? Okay, so a few weird things going on that we should preface any solving with. First off, we're talking about exponential decrease, decay. So for that, there's actually a different formula, pretty similar to the growth formula. It's going to be y equals ce to the negative kt. That negative gives us decay instead of growth. Now, on this problem, they wanted to know at what elevation is the pressure half of the pressure at sea level. So just in terms of input and output variables, we have atmospheric pressure decreasing as a function of elevation. So pressure is the y values, the output values, and the input value then is elevation. So in this scheme, elevation is actually your t value. In this problem, elevation is taking the place of time. So that means that in this problem, we're trying to solve for this t value because we want the elevation here. So that's one other piece of trickiness that you're going to have to work around. In order to get this t out of the exponent, you may need to use logarithms or something like that that you learned in a past course. Now, the only other thing that's a little bit tricky here is if we're looking for t, that means we need to plug in things for everything else. And you might be wondering, well, okay, the c value would be the that would be the pressure at sea level, but they didn't tell us the pressure at sea level. They did tell us that our target pressure is going to be half of whatever that sea level pressure is. So you're going to need to find a clever way to fill in some of these values when they didn't give you all of the information. Let's see if you can sort that out. So pause the video and give this one a shot. All right, so finding values for c and y is kind of the first piece of trickiness on this. Since we don't know what the actual pressure at sea level is, we can't put anything in for c. But we know that y is half of whatever that c value is. So to be a little bit clever, I'm just going to use 1/2 c for my y value. And I'll just leave this c the way it is. So now the other piece I need to fill in is the k value. That's going to be the rate of decrease as a decimal. So we're just going to say e to the negative 0.125 times t. And now I've got everything in place I need in order to solve this equation for t. So first thing we need to do is get the exponential part by itself by dividing both sides by c. And presumably the atmospheric pressure is not exactly 0 at sea level. Otherwise, some very interesting things would be happening to, well, all of the living creatures at sea level. So we'll just assume this is non-zero and assume that we can divide both sides by it. So if I do that, I've got 1/2 equals e to the negative 0.125t. Now to get the t out of exponent land, I'm going to need to take the log of both sides. Since I've got e as my base, I'm going to use ln. So I'm going to have ln of 1/2 on the left side, and on the right side, my exponent pops out. I've got negative 0.125t times ln of e, but ln of e is just 1. So I really just end up canceling out the e over there and getting negative 0.125t. At this point, all I need to do is divide both sides by t. So let me go to the calculator for that. And let me just move this so I can see. Let me do fraction ln of 1/2. I'll just do that in a parentheses. There we go. And now on the bottom of my fraction, I've just got negative 0.125. And that comes out to about 5.545. And that's the elevation, so that's going to be in units of kilometers. For our final boss battle here, we're going to go back to population growth. So for a period of time, an island's population grows at a rate proportional to its population. So again, we've got our exponential sort of language here. If the population was 785 7.8 years ago, and the current population is 1,141, in how many years will the population reach 1,574? All right, well, we can at least start, and we'll do this one partially together here. We can at least start with our exponential growth formula since we are growing. So that's a good starting point, y equals ce to the kt. Now, ultimately in this one, we're trying to figure out, they're saying in how many years. So ultimately we're solving for a t value, which means we need to plug in things for y, c, and k. And they gave us the current population, 1141. But that's all we have right now. Well, actually, no, they gave us the target population too. They gave us 1,574. So we actually start with c and y. The tricky part, though, is they didn't give us the rate. They didn't give us k. So in order to figure that out, we're actually going to need to plug some other things in first. Now, if I want to find the k value, I'm reading this here. They said the population was 785 7.8 years ago. So we can use that past value to help us solve for k. So the way to start this one off then, for my initial y value here, I'm going to use this old target value of 785 because the population was 785 7.8 years ago. So that means I can use 7.8 as my t value if I use 785 as my y value. So for my c value, I can use 1141. That's the current population. And the k we're going to solve for first. The t value I can use here again is this 7.8 years ago. So for that, since it's 7.8 years ago, I am going to have to go back in time for this. So I'm going to have to use negative 7.8. So we'll have e to the negative 7.8, and then k is what we're solving for. All right, well, in order to find this, let's divide both sides by 1141. And just like before, to get rid of the e, we're going to take the log of both sides. So I have negative 7.8k equals ln of all this stuff here. And then I'll just divide all of this by negative 7.8. So let me go in the calculator and do that. Here's my Desmos. And I've got, let me just do a big fraction, ln parentheses fraction 785 divided by 1141, close that parentheses, and down here we're going to have negative 7.8. 7.8, there we go. So there's the crazy value we get. Now, one little point of information here, we've got to be careful. There's a temptation to round this off and be like, oh, well, if this is the AP exam, I'll take it out to 3 decimals. You don't really want to do that, though. You want to actually, if you can, not round on the middle steps, but instead store them as values and use those values on the calculator. The trouble with rounding off in the middle is these exponential functions grow so quickly that even just a small difference more than 3 decimals out can totally skew your answer. So what I'm going to do instead, I'm going to say that k is equal to a, and I'm going to let a equal whatever I got on the calculator. So in this case, what I'm going to do is I'm just going to arrow back here to the beginning, and I'm just going to write a equals all of this stuff. And now, whenever I write a, I can get that crazy value back and just use it. So I've got that stored. And I'll just make a note here that it's approximately equal to 0.0479. But again, I'm just rounding this off for cosmetic purposes. I've really got it stored on my calculator. All right, so we found the k value. Pause the video and see if you can take this one the rest of the way and see how many years it takes this population to grow to 1574. All right, let's see how that went. So using our y equals ce to the kt formula again, this time for y, my target population is 1574. I'm still using 1141 as my current population, and now I have a k value to put in here. So I'll have e to the, and I'm going to call this again a for k times t. Solving this now, same kind of steps we did over here. Divide by 1141. Take the ln of both sides. So we have ln of that crazy fraction equaling a times t. And now I'm just going to divide both sides by a, which I'm going to do on the calculator. So I've got fraction ln, open a parentheses, fraction, 1574 divided by 1141, all of that over, and now I can just write a, and it'll do that for me. So that comes out to about 6.710 if I take it to 3 decimals, and that is going to be in years. So that's it for this lesson. Hopefully your understanding is exponentially better than when you started and in a growth, not decay direction. Till next time, Mr. Sutton signing off.